What's up, everybody? Day 6. I'm going to talk about a couple things today, repeating decimals and then also rewriting sums before we can calculate the actual value of infinite sums. So let's get started with these 6 review problems real quick. Run through them, pause, run through them, see what you come up with, and then we'll go over them here in a moment. Alright, so let's do this first one here. First thing you should do is recognize that this is an arithmetic sequence, which means we have a common difference d right there, that 4. And this 2 is our first term, a sub 1. So in order to find the sum of the first 7 terms of this sequence, we need to figure out the first term and the last term, because then we can use our summation formula for an arithmetic sequence, which is S of n equals the number of terms divided by 2 multiplied by the first term plus the last term. So let's find a sub n, which we have the explicit formula right there, and we want to find a sub 7. So more specifically, let's find a sub 7, and we have 2 plus 4 times 7 minus 1, just plugging in 7 for n right there. And we can simplify this. 7 minus 1 is 6, times 4 is 24, plus 2 is 26. So the 7th term is 26, which means if we want to calculate this sum of the first 7 terms, all we need to do is take the number of terms, which is 7, divided by 2, multiplied by the first term, which is 2, added to the last term, which is 26, and let's simplify it. And what can we do to simplify this? Well, 2 plus 26 is 28. 28 divided by 2 is 14. So I have 7 times 14, and 14 is 7 times 2. So 7 times 7 is 49, times 2 is 98. And you can come up with that another way. That's just how I do my mental math. So that first sum there is 98. And let's take a look at the next one here. Next, we are looking at an infinite sum. It is arithmetic, and our common difference d is negative, which means that this infinite sum is negative infinity. No work needed. If it's arithmetic, and the common difference is negative, and it is an infinite sum, it will always be negative infinity. Alright, what about this one here? Well, same idea. We are looking at an infinite sum. It is arithmetic, and the common difference now is positive. Therefore, this sum is positive infinity. So those are our 3 arithmetic problems. Now let's do our 3 geometric problems here. First one, we're looking at a partial sum, so we want to find S sub 10, the 10th partial sum of this geometric series. And to do so, we need our partial sum formula. S of n equals the first term times 1 minus our common ratio r raised to the power of n divided by 1 minus our common ratio r. So we have all this information at our fingertips. So we want the 10th partial sum, which means we will take our first term, which is that 3. And we'll multiply it by this fraction, 1 minus our ratio, which is negative 4. And that ratio is raised to the power of n, which is 10. Divide that by 1 minus our ratio, which again is negative 4, which will make that plus 4. Notice on the bottom it is plus 4, but on the top you cannot combine those two negatives because negative 4 is being raised to the 10th power, so you cannot just get rid of it. So let's go ahead and punch this into our calculator real quick to find the sum. If I'm typing this in, I would type it as 3, open a parenthesis for the numerator, 1 minus, open a parenthesis, negative 4, close your parenthesis, power, caret button, 10, close the parenthesis for the numerator, divided by, open a parenthesis, 1 plus 4. You could just write it as 5, whatever you want to do, then close that original parenthesis, lied, that was an extra one, hit the enter button and see what you get. I got this ridiculously large number, large negative number, so negative 629,145 for that sum. And you should be able to verify that on your calculator by actually calculating the sum of this sequence, if you remember how to do that. Not going to go through that now. Let's go ahead and do this next problem. So now we are looking at an infinite geometric sum. First thing I do when I'm looking at an infinite geometric sum is I look at my common ratio r, and it's a good thing I did because my common ratio r is 16, which is greater than 1, which means that this sum is simply infinity, because the 5 is positive. If that 5 were negative, it would be negative infinity. But anytime that ratio is greater than 1, the infinite sum there will always be infinity or negative infinity, depending upon the sign of the first term. So now let's go on to this last problem right here. This is the interesting case when your r value is between positive 1 and negative 1. Oop, right in that spot right there. R is less than 1, but it's greater than negative 1. That's when we get to use our infinite summation, first term divided by 1 minus our common ratio r. And so let's do that now. What is our first term? Our first term is 1/4 divided by 1 minus our common ratio r, which is 3/4. Well, numerator, let's leave that as 1/4. Over 1 minus 3/4 is 1/4. And hey, look, this infinite sum is just equal to 1. So there you have it, 3 arithmetic series, 3 geometric series, some infinite, some finite, but we found the sum of each. Now what we're going to do with the rest of the time today is we're going to look at rewriting some sums before we calculate their sums, before we're able to use our summation formulas. And then also we're going to look at how we can write repeating decimals in summation form as the sum of geometric series. So first thing I want you to do is rewrite this sum and then actually calculate the sum. Well, to do that, you need to recognize that 1 over 3 to the n minus 1 is exactly the same as, I'll rewrite this sum real quick, n equals 1 up to infinity right there. If I can rewrite that fraction, I can just rewrite it as 1 over 3 to the power of n minus 1, like that. In this instance, it looks a little more familiar to us. Think about the fact that if you have that n minus 1 on the 1 there, it makes absolutely no difference. And so I can pull that out and rewrite it as such. And now I can see that my common ratio r is 1/3. And my first term, a sub 1, is just 1. You need to think of it as the coefficient out front there that's kind of just hanging out, going along for the ride. Now it's an infinite sum, and my ratio r is between negative 1 and positive 1, so I can calculate this sum, this infinite sum, s sub infinity, by taking my first term, 1, and dividing it by 1 minus my common ratio, which is 1/3. So I get 1 divided by 1 minus 1/3 is 2/3. 1 divided by 2/3 is the same as 3/2. And there you have it. Rewrite that sum and found the infinite sum. Alright, well, quick reminder here, if you have x squared times x cubed, something like that, you probably know that that is x to the 5th. But I want you to think about what you're actually doing. You took the two exponents with the same base of x, and you added them together. So you could, if you wanted to, for some reason, write this as x to the power of 2 plus 3. And for example, if you had something like, let's say, n to the power of 2 plus 3, if you wanted to, you could go the other way and you could rewrite that as n squared times n cubed. Keep that in mind when we go to this problem right here, because we have an issue. So we have an issue when we look at this, because normally we want our exponent here to say n minus 1, and currently it says n plus 2, which actually is a problem if we want to use our typical summation formula. So let's think about pulling out pieces of this so that we could be left with n minus 1. Now, first off, I'm going to write my summation, n equals 1 down there, up to infinity. Now again, think about what our goal here is. Our goal is to get this expression, 1/2 raised to the power of n minus 1. And currently it's raised to the power of n plus 2. So what would we need to have out front here to combine these two powers these two 1/2 bases raised to powers, to combine these two to get an n plus 2. How many would we need to add? Well, if the idea is that we're just adding exponents, then we need to add however many would get us from -1 up to +2. And that would be 3. And think about, again, what that means. Again, we're using the same idea here as x squared times x cubed equals x to the 2 plus 3, which is x to the 5th. It's that same exact idea here. Imagine we went back in. 1/2 cubed times 1/2 to the n minus 1 must equal 1/2 to the power of 3 plus n minus 1, which is, if you simplify that, -1 and a +3, 1/2 to the power of n plus 2, which is what we've started with. So we didn't change anything at all. So I'm going to get rid of this real quick, and I'm going to continue to simplify this before we actually go and calculate the value of this. That 1/2 cubed right there, that is our first term, but let's write it a little better. 1/2 cubed is the same as 1/8. So I'm going to write this as the sum from n equals 1 up to infinity of, whoops, not 1/2, but 1/8 times 1/2 to the n minus 1. And now that it is in the familiar form, now we can use our summation formula. S sub infinity is going to equal the first term, 1/8, divided by 1 minus our common ratio of 1/2. And again, we can simplify these by hand. I have 1/8 divided by 1 minus 1/2 is 1/2. So 1/8 divided by 1/2 is the same as 1/8 times 2. And 1/8 times 2 is 2/8, or more commonly known as 1/4. And again, you could check all of this on your calculator by finding the summation, and you would indeed get 1/4. Or rather, you really couldn't on your calculator, but I guess you could plug in a really large number for n on your calculator and see if that works. But we don't need to, because we did it algebraically there. Alright, so one last thing I want you to think about here is if you end up with a problem like this, where our starting n term is not 1 as we are used to seeing it. If that's the case, think about what you would need to do to it to make it 1. Let's make a little algebraic substitution, because we want that to say something equals 1. So let's rewrite this in terms of some other letter. Instead of n, let's rewrite this in terms of some k, because we want that bottom term there to be 1, the first term, k equals 1. So let's do that limit up into infinity, and then we can have our 2 times 1/3. But then here's the thing, we can't put an n up here, because now everything is in terms of k. So we need to think about what the relationship between k and n is. Well, clearly if k equals 1 and n equals 0, then k is going to equal n plus 1. When n was 0, k was 1, and so we added 1 to it, which then allows us to say, well, what is n? Well, if we subtract 1 from both sides, we get k minus 1 equals n. So up here, instead of writing n, we can write k minus 1, which is what we wanted, because we needed our exponent to be in the form of the variable minus 1. And now we have it, so we can find our infinite summation in the same way by taking our first term, 2, and dividing it by 1 minus our common ratio, 1/3. So again, we can do this by hand. 2 divided by 2/3. Again, think of that as 2 times, instead of dividing by 2/3, we can multiply by 3/2. 2's cancel, and we're left with just 3. Alright, so now let's do one where you combine these two ideas, and then we'll see where we can take it. So this problem might look scary, but again, we're just going to use both of those two ideas we just talked about. So what can we do? Well, first thing I'm going to do is I'm going to get the power in the denominator and the numerator to be the same by pulling terms out of the numerator. Because once they're the same, then I can write it as a single exponent rather than numerator and denominator separately. So since the bottom is n, I'm going to make the top equal to n as well. So if we want the top to just be n, how many powers of 5 do I need to pull out? Well, I need to pull out 3 powers of 5. and then that will leave me with 5 to the n over 7 to the n. Again, think about if I multiplied that 5 back in, then I would increase the power inside that parentheses by 3, so I'd end up with that n plus 3. So there we have that. It's looking a little more like our familiar geometric series there. But again, I want to write the exponent as the same for the numerator and the denominator. So instead of 5 to the n over 7 to the n, I'm going to say 5/7 to the n. But I still have this n equals 0 and this infinity up top. So now I'm going to adjust that index. Rather than starting from n equals 0, I want to start from 1. Or another way you could think about it is, instead of that n up there, I want that to be something minus 1. So here's our summation going to infinity. We have our 5 cubed out front, which maybe I'll just rewrite as 125 right now. But then I have 5/7, and I want this exponent to be in the form of something minus 1, because then I can use my formulas in the normal way. So I want k minus 1 to equal n, which then means that n has to equal, sorry, it's not what I meant to say, n does not have to equal, k has to equal n plus 1 if I add 1 to both sides. And then I can say, alright, if n is starting at 0, then k is starting at 1. And now it's familiar again, and I can use my summation as I normally would. So this will equal the infinite sum, which is going to be the first term, 125, divided by 1 minus my common ratio of 5/7. So let's simplify this a little bit, see if we can do it without our calculator. Maybe we'll need one, who knows. 1 minus 5/7, well, I can rewrite that as 2/7, and yeah, I'm totally going to use a calculator for this. And when you crunch that number, you get 437.5. So we did two things in this problem. We adjusted the index so that we were starting not with 0, but with 1, and we pulled out that a(1) first term so that we could get it into this familiar term that we're used to seeing it. So our summation formulas would work as normal. So that kind of hits it for a little bit of review and a little bit of new stuff. And now we're going to talk about a really cool application of geometric series that I love to talk about. And now that I went into all that, I lied. Here's actually one more for you to do. So why don't you do this real quick. So calculate this sum, and then we'll go on to the new cool thing. Let's actually make it a little more interesting. Let's not make that a 1. Let's make that a 2 right there. Find this infinite sum. 2 to the n plus 2 over 3 to the n. Starting at n equals 0, going up to infinity. Let's try that real quick, and I'll show you here in a moment. Okay, I burped. That means it's time to go. So, first step, let's get the power of the numerator and denominator to be the same. And to do that, I need to pull out these two powers of 2. So I'm going to pull out that 2 squared to the front. And what will I be left with? I'll be left with 2 to the n over 3 to the n. So again, let's rewrite this once more. N equals 0 up to infinity. I pulled the 2 squared out, so that's a 4. And then I have 2/3 to the power of n. But I don't want this to be to the power of n, and I don't want that to be n equals 0. So I'm going to make an adjustment. I'm going to say, well, I want this to be a 1. So let's call this some k instead of equal to 1. Now if k equals 1 when n equals 0, let's say that k equals n plus 1. And if k equals n plus 1, then n equals k minus 1. And so up top here, instead of n, I'm going to have k minus 1. Because now it's in the form I want it to be, and now I can calculate this infinite summation. So first term divided by 1 minus my ratio, which is 2/3. So I have 4 divided by 1 minus 2/3 is 1/3. Dividing by 1/3 is the same as multiplying by 3, and so 4 times 3 is 12. And now we can go on to the new stuff. Alright, now here's the deal. Growing up, you've always been told that 0.9999999999999, well, let's just call that 1. And we see that and we always say, well, yeah, that's 1, clearly. Look how close it is. But here's the thing. I'm going to show you that not only is it really, 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 really close to 1, it is mathematically equivalent to 1. Now, the first way I'm going to show that to you is kind of just like a little trick to get us there, but then I'm going to do it more rigorously. Now, in your calculator, type 1 divided by 9. If you do so, you will get 0.11111111 on your calculator. However many ones your calculator will tell you, that's what it will tell you. That's if you do 1 divided by 9. Now do the same thing with 2 divided by 9, and your calculator will say 0.2222222, and that's going on forever. And same thing with 3/9. It's going to say 0.333333333, and it would keep saying it forever if it could. And it's going to do the same thing with 4/9 and 5/9 and 6/9. So if we continue this pattern down, imagine you did 9/9. Well, we know that 9/9 is 1. But from the same pattern, shouldn't it also be 0.9999999 going on forever? Yes, it should, and that's why these two things are absolutely equivalent. 0.9 repeating not only is very, very close to 1, it absolutely is 1. It's the same idea with this guy right there. We know that 0.3 repeating, or if you want to write it as 0.3 with a little bar above it, we know that that is the same as 1/3, or at least we think we know. We've been told that it is so, but we're going to actually prove that it is now. And so to do so, we need to think of this number in kind of a special way. What I want to do is I want to think of each one of these 9s separately, and I want to think about how we could add it together. Well, let's think of that first 9, 0.9. And then let's add to that, there's our first 9. How do we add just this 9 in the box to it? Well, I couldn't just say plus 0.9, because 0.9 plus 0.9 is 1.8, and that's not what I'm looking for here. I need that. What I want is to add these two numbers together. That will give me just 0.99 when I add them together. Well, to do that, I could add 0.09 to it, because 0.9 plus 0.09 is 0.99. And now I want to do the same thing with this next 9. And to do that, I would just need to put another 0 in front right there. And I could do the same thing with the next one, except put an additional 0. And I could keep doing this forever. And what we have is a geometric sequence. So let's think of these as fractions. 0.9 is the same as 9/10. Plus 0.09, well, that is 9/100ths. And 0.009 is 9/1000ths, etc., etc., etc. In each instance, I'm increasing by a power of 10 in the denominator. And that pattern is going to continue forever for all of the 9s, which are continuing on forever. And so let's think of this in terms of a typical geometric sequence, series rather, that we've been doing in class. Well, my first term is 9/10. And what's my common ratio? Well, I'm increasing by a power of 10 in the denominator each time. So my ratio is 1/10. And I need to raise it to the power of n minus 1. And if we want to add all of this up, we'd be looking at an infinite summation from 1 to infinity. And this summation would represent the decimal 0.9 repeating. Plug in some n values and convince yourself that that's true. Right? You plug in n equals 1, you get an exponent of 0, so the 1/10 goes away, and you're left with 9/10. If you plug in an n value of 2, you get an exponent of 1, and so we're taking 9/10 and multiplying it by 1/10, which gives you 9/100ths. And then the same thing, each instance, by having that 1/10 as our ratio, we're increasing the number of zeros we're plopping in front of that 9. And so we can calculate this in the same way we calculate any infinite series for a geometric series. We take our first term, which is 9/10, and we divide it by 1 minus our common ratio, which is 1/10. And what do we get? Well, we get 9/10 over 9/10, which we know is 1. So mathematically speaking, 0.9 repeating is not just very, very close to 1, it is mathematically equivalent to 1. So that's, I think, really cool and very interesting and kind of mind-boggling in a way. And let's do the same thing now with this decimal point. 2-3 repeating. So 2-3, 2-3, 2-3, 2-3, etc. forever. So again, let's break it up into pieces like we wanted to before. Now, the first piece, let's make 0.23, the stuff that is repeating. And then what would I need to add to that? Well, I'd need to have 2 zeros for the 2-3 that I already used, and then I'd want a 2-3 afterwards. And then for the next one, I need to have 4 zeros to get rid of all of those 2-3s I already have on there, and then I could have my 2-3. And then for the next one, same thing, but 2 more zeros again. And this pattern of increasing by 2 zeros each time is going to continue out. And so let's, again, think about these as fractions. Well, the first one is going to be 23 over 100. And then the next one is going to be 23 over 10,000. If I want to put these 2 zeros right there, I need to increase that denominator by 2 zeros. And then the next term would be the same idea. 23 divided by, if I had 4 zeros there, I now have 6 zeros right here. And so now we have 23 1/millionths already, and that's going to continue forever. So we can write this as a series. We can say this series from n equals 1 up into infinity, with the first term, 23 over 100. And each time I want to increase the denominator by 2 zeros, which means I need to have 1 over 100 there, and I need to raise it to the power of n minus 1. And that will equal this infinite sum with the first term, 23 over 100, divided by 1 minus my ratio, which is 1 over 100. And we can simplify things. Let's leave that numerator the same, 23 over 100, divided by the denominator now. If we're doing 1 minus 1 100th, I'm left with 99 100ths. And look, those hundreds cancel off, and you're left with 23 divided by 99, which is really cool. Anytime you're dealing with a decimal that is repeating like that, you can always express it in terms of a denominator with 99. So for example, if you have 0.46572, that is going to be the fraction 46572 divided by 99999. You're always going to end up with the same number of 9s in the denominator as you do for the digits up top, which is crazy and can be proven using geometric series. Have fun with that.